So let's look at different types of organic chemistry molecules we have and go from simple to more complex. So hydrocarbon are your most simple organic molecules. They are covalent molecules that contain only hydrogens and carbons. They can contain single, double, or triple bonds, but they only contain carbon and hydrogen. The single, double, and triple bonds only occur between carbon and carbon, not carbon and hydrogen. Why is that? Well, if we think about the structure of hydrogen, hydrogen has, if we do like a quick dot diagram, it only has one electron. And in order for it to have a full shell, it only needs one extra electron. And so that one extra electron will be shared from the carbon that it's bonded to. But it can't bond any more than that because it doesn't have any other electrons to be able to share and form a covalent bond with. So that's why the double and triple bonds only occur between carbon. Because if we think about carbon now, it's got 4 electrons, and so it can form a single bond by sharing only one electron. It can form a double bond by sharing both of those electrons, or a triple bond by sharing all 3 of those electrons. The reason it doesn't form a quadruple bond is essentially because it wouldn't leave room to extend the chain, because it needs to be bonded to another carbon in order to be able to extend the chain going on. Cool. So going back to the naming convention, how do we name hydrocarbons? We name them according to first the longest carbons, the number of carbons in the longest carbon chain. So we have different prefixes that we use. The first few are a little confusing, but the other ones make a lot of sense if you've done any sort of maths. So 1 carbon is meth, 2 carbons is eth, 3 is prop, 4 is bute. There's lots of different weird and wonderful mnemonics that people use. The one that I've heard the most often is monkeys eat purple bananas. So monkeys eat purple bananas. But there's all sorts of different ones. Choose whichever one you like. So the first 4 are a little bit weird, but then after that, it's just your standard math type prefix. So 5 is pent, like pentagon. 6 is hept, like 6 is hex, like hexagon. 7 is hept, like heptagon. 8 is oct, like octagon, and so on and so forth. So really, as long as you remember the first 4 being slightly different, everything else makes sense. So if we look at the molecules that we have here on our right-hand side, here we have a carbon that is just by itself. So that is just going to be meth. And then the suffix of it is basically going to depend on whether we have single, double, or triple bonds. So that's basically what is being highlighted here. So if you have a single carbon-carbon bond, so all of them are single carbon-carbon bonds, then you have a suffix of "ane". If you have a double carbon-carbon bond present, then we use "ene". If you have a triple carbon-carbon bond, then we use "ine" with a Y. So we use the combination of the prefix and the suffix, which tells us how many carbon-carbon double, single, double, or triple bonds there are, in order to put everything together. So now let's use that information to name these 3 molecules here. So you have a most simple molecule, so just 1 carbon. So just 1 carbon means it's meth, and it's only a single bond, so it's going to be methane or methane. Now if we look at our next one up, this one here, it's 1, 2, 3, and 3 carbons is prop, so it's going to be prop. And now if we look at whether we have single, double, or triple carbon bonds, we can see that we do have a double carbon bond. So that means that's going to be propene instead of propane because of that double bond there. So propene. You might also need to number where your double or triple bonds are, because they can be in different locations throughout your carbon chain. In this case, it doesn't really matter because there's only really one place for that double bond to go. So don't worry about it too much, but just to flag that sometimes you need to specify where that bond is. Then finally, we have this one here, which is 1, 2, 3, 4, 5, 6. So 6 going back to here is hex, like a hexagon. And it's all single bonds, so it's going to have that suffix of ane again. So this is hexane. Awesome. So with any of your anes, your single bonds, you don't have to specify, 1, 2, or 3, because obviously there's all single bonds. You don't have to specify any numbers like that. So all three of these types, whether you have a carbon-carbon single, double, or triple bond, they're all called hydrocarbons, and within them they have sort of individual families. So you have your alkanes, which are your single bonds. You have your alkenes, which are your double bonds, and your alkynes, which are your triple bonds. So kind of three families within your hydrocarbons. Cool. That basically summarizes that. So alkanes, single bonds, alkenes, double bonds, alkynes, triple bonds. There's also this terminology of a functional group. So your functional group is basically the whatever is within your organic compound that makes it special or gives it some sort of different property. So in an alkane, you only really have one type of bond. So your functional group or functional bond is just your single carbon-carbon bond. In your alkene, the thing that's different that makes it special is having that double carbon-carbon bond. And in an alkene, your functional group is that triple carbon-carbon bond. Note that it says at least one, so you can have more than one, and it still fits into that group. Great. So just going into a little bit more detail about each of those groups. Your alkanes, as we mentioned, single bonds between your carbon atoms, the suffix of ane. Something that's really useful is this general formula here. So Cn, so N being your number of carbons, and then H is 2N plus 2. So basically that just gives you a way to predict the number of hydrogens that would be present given a certain number of carbons. So for example, if I have methane, methane is carbon 1, so C1. So my H would be 2 times 1, which is 2, plus 2, which is 4. So that's methane. Propane, so C3, and then my H is going to be 2 times 3, which is 6, plus 2, which is 8. So it's relatively okay for smaller hydrocarbons to just even be able to draw them out and very easily predict what's going to happen. But this becomes a lot more useful if you have really big atoms where you don't really know. So for example, with the carbon 15 that we were looking at before, sure, you can draw 15 carbons and count them out, but it's a little bit annoying. So we can use our 2n plus 2 rule and say 15 times 2 is 30, plus 2 is 32. So that's going to be our number of hydrogens in an alkane with 15 carbons. So it's just a useful thing to remember. Makes your life a little bit easier. Your alkenes, as we mentioned, double carbon-carbon bond, ends in the suffix of -ene, and its general formula is C2H2N. So C2H2N, so you just double your carbons, you don't add anything to the end. So ethene is your simplest alkene. You can't have a methene because then you don't have 2 carbons to have a double carbon-carbon bond with. So ethene is your simplest. And then here we can see we have butene, so 1, 2, 3, 4. To be even more accurate, actually, in naming butene, we'd actually want to name this but-2-ene. And this is just specifying exactly where that double bond is within your compound. Because theoretically, you could have a compound that looks like this, where your double carbon-carbon bond is actually on carbon number 1 rather than carbon number 2. So here, if we label our carbons in order, we can see that the double bond is on carbon number 2, whereas here, if we label our carbons, the carbon bond is on carbon number 1. So it's really helpful to be specific about exactly where your double bond is by putting a number in front of the suffix. So this one would be but1-ene, and this one would be but2-ene. Again, these are going to be isomers of each other because they have the same structure, same molecular formula of C4H8, but they have a different structural formula because of where that double bond is located. And as we mentioned, different structural formula means it's going to likely have a different structural formula means it's going to have different physical properties, and it's going to interact with other molecules differently. So that's why it's so important to know that. And then finally, we have our alkynes. So our alkynes ending in the suffix "-ine. Our general formula is C2H2N minus 2. So hopefully you kind of see a pattern there. So you start with plus 2, then you get rid of the plus 2 and go to 0, plus 0, and then you go minus 2. So as you add a double bond, you take away 2 hydrogens, essentially. Or as you add a carbon bond, you take away 2 hydrogens. So here, our most simple alkene is going to be ethene, C2H2. Then you have butene, and again, remember to be specific with this. So it's actually going to be but1-ene, or -ine rather, because your triple bond is on carbon number 1, where it could be on carbon number 2. So the rule for do I need a number or not is basically, could this bond be somewhere else? And if it can be, then you need to specify. Cool. So that's basically it for your hydrocarbons. We'll just go through we kind of went through it generally, but just a more systematic way of naming your compounds. So your steps are to identify the longest carbon chain. The important thing is that the longest carbon chain has to contain the functional group. So in what we talked about before, it has to contain the double bond or the triple bond. Then you want to determine the family that it belongs to. So that's essentially your suffix. So is it an alkane, is it an alkene, is it an alkyne? Then you number the carbons, and with the numbering of the carbons, you want to start with the side that is closest to the functional group. So in this, I could number my carbons 2 ways. I could go 1, 2, 3, 4. And that would be, numbering it with the side that's closest to the functional group. But I could also alternately label it 1, 2, 3, 4 like this. But the reason why the red is correct and the blue is not is because the red demonstrates your numbers being in order closest to the functional group. So numbering your carbons, that's really important, because otherwise you'll get an inaccurate IUPAC name. Then you put it all together. You have your prefix from your number of carbons and then your suffix from the family it belongs to, and you put it together. So let's go through some questions. So I'm going to give you a little bit of time to answer in the live chat, and I'll be there to just say whether you're right or not and give you some guidance along the way. So have a quick think about this, maybe 30 seconds or so, and then we'll quickly run through it. Okay, hopefully you've had to think about what this might be. So let's go in order of our naming steps. So what is our longest carbon chain? Our longest carbon chain is 1, 2, 3, 4 here. What family does it belong to? Well, there's only single carbon-carbon bonds, so that means it must be an alkane. So now I'm going to number my carbons. There's no functional group, so no double or triple bonds, so it doesn't really matter which end. So 1, 2, 3, 4. And now I need to put it together. So 1, 2, 3, 4, if you remember, is bute. So it's going to be bute. And then because it's an alkane, it's going to be butane. Great. Let's have a go at this one. Again, I'll give you guys maybe 30 seconds or so to have a think about it. Put your answer in the chat and I'll be there to respond and give you some guidance. Alrighty, let's go through it. So again, longest carbon chain is going to be 1, 2, 3. What family does it belong to? Well, now there's a double bond, so it's going to be an alkene. Now I need to number my carbons. Remember to start from the side that's closest to your double bond. So I'm going to start from here and go 1, 2, and 3. And therefore, we've got 1, 2, 3. 3 is prop. And because I have my double bond, it's going to be propene. You might be tempted to think it's going to be prop-1ene, and certainly you're not exactly incorrect by saying that. But whether your double bond is here or here, it's still going to be on carbon number 1, because if it was here, then we would label starting from this side and say that this is 1, 2, 3. So it doesn't change how we would name it, it doesn't change the structure. So you don't actually need to include the 1 there. So remember the rule of thumb is if I move, can I move this somewhere else and will it change the name? I can move it somewhere else, but it won't change the name. So I don't need to include the number. Great. Let's have a go at this one. So I'll give you guys 4 minutes to do this because there's 2 of them. And this is number 1, this is number 2. So let's have a go at that. All right, good work, guys. So hopefully you put your answers in the chat. So let's go through our normal order. So we've got 1, 2, 3, 4. That's our longest carbon chain. I've got a double bond, so that means it's going to be in the alkene group. I'm going to order starting from my closest side to the double bond. So 1, 2, 3, and 4. Now putting it together, 4, as we mentioned, is bute. And now I have a double bond. But here I have a double bond that could be somewhere else. It could be on carbon number 2. So I need to say it's but-1ene and specifically mention the fact that I have that double bond on 1 and not 2. Now if we look at carbon number 2, very similar. Longest carbon chain is 1, 2, 3, 4. It's got a double bond. It's also an alkene. Need to number my carbons. Doesn't really matter which side you start with this one, but let's just go with the same side for VCEs of it. So 1, 2, 3, and 4. Again, 4 is bute, so B-U-T. Then carbon number 2 is where my double bond is. So this is going to be but-2-ene rather than but-1-ene. So this is really just to highlight and make sure you know the difference between where your double bond or functional group is located and the importance of mentioning that when you actually name your compound. Cool. So now let's look at another functional group. So it doesn't always stay as simple as just having carbons and hydrogens. Sometimes you have other functional groups. So in this case, we have an OH or an alcohol. Sometimes so it's an alcohol in terms of what we call the group, but the OH itself is actually called a hydroxy group. So it's not called an alcohol group, it's a hydroxy group. A little confusing, I know, but the overall family is still called an alcohol. So alcohols end in the suffix -ol, so very similar to how alkenes are -ene and alkynes are -ine, alcohols are -ol. So in this example here, we have methanol, where you have an OH off your carbon. You have propanol, where you have an OH off your carbon here. Once again, it's really important to specify where your group is. So here, your OH is on this carbon here, but it could be on this carbon in the middle. So you need to specify not just that it's propanol, but actually that it's propan-1-ol. So very similar idea to when we had to specify where your double or triple bond is. You need to specify that it's propan-1-ol. I'll just make a note that sometimes in like the older IUPAC, you will also see 1-propanol. That's also acceptable, really. It kind of conveys the same idea, but I will say that using the convention of having the 1 in the middle just before your prefix is more conventional, but just that you might see that in other cases. So just keep that in mind. So that's propan-1-ol. Cool. We sort of mentioned this before, but this is just to highlight once again. When you're numbering your carbons, you want to number with the lowest number. So that's why we number closest to our functional group. So if we look at these black numbers here, when we go to name our compound, if we go through our process, it's 1, 2, 3, 4, 5. 5 is pent. Then we have our functional group is a hydroxyl group, therefore it's an alcohol, and the hydroxyl group is on carbon number 1, so it's going to be pentan-1-ol. So if we use those green numbers, we can go through that exact same process. So 5 carbons, so it's still going to be pentan. It's still an OH, so it's still going to be ol, but instead, because we've named it the opposite way, we'd have pentan-5-ol. But the important rule of thumb with IUPAC naming is that we want the smallest numbers possible, because it just makes it a little bit easier when we're drawing out or trying to visualize the molecule using its name. It's easier if we have a smaller number. So that's why we prefer pentan-1-ol, and that's also why we number our carbons closest to the functional group, because if we number closest to the functional group, then that will automatically give us our smallest number without us having to put in too much extra effort into anything. Cool, that just highlights that once again. All right, so it's good to know some important properties about alcohols. And this is where we tie it back into our hydrogen bonding that we mentioned before when we talked about intermolecular bonding. So the presence of an OH, so this OH that we have here, allows hydrogen bonding to occur between alcohol molecules. So why is that? Well, remember your hydrogen bonding occurs between fluorine, oxygen, and nitrogen, and a hydrogen molecule. So because you have this hydrogen here, if you have another OH from another alcohol, then these are going to form hydrogen bonds there. So what does that OH mean? Well, the OH means that you're going to have higher boiling points because remember, hydrogen bonding is much, much stronger than dispersion forces, which would be present in your simple hydrocarbons. And therefore it requires a lot more energy to break them apart, meaning you have a higher boiling point. It also means that some of your smaller alcohols are going to be soluble in water because they have a polar component. And remember, like dissolves like, so your polar water will dissolve the polar OH part. As your alcohols get bigger and they have a bigger and bigger normal hydrocarbon region, so as this area here gets bigger and bigger, they're going to be less soluble because percentage-wise, less of the molecule is actually polar. Cool. All right, so this is also just mentioning some trends. So boiling point will increase with alcohol size because your non-polar proportion increases. So that means you're going to have stronger and stronger dispersion forces as your alcohol gets bigger. And stronger dispersion forces or any intermolecular bonding will increase your boiling point. And as we talked about, your solubility decreases because your non-polar bit of your molecule increases in size. So this bit gets bigger. It's no longer going to be as soluble in water. All right, our next functional group is our carboxyl group, or our COOH. The series or the family is known as a carboxylic acid, and the suffix is actually oic acid. So the COOH is actually a carbon that's double bonded to an oxygen and also bonded to an OH group. So this is your functional group here. So then you have methanoic acid, very simple here. You've got 3 carbons, so now it's propanoic acid, and so on and so forth. The fun thing about carboxylic acids is that you don't need to worry about numbering them because your carboxylic acid group is always going to be at the end. Because you can imagine your carbon can only have 4 bonds. 2 of them are taken up by an oxygen. 1 is taken up by the OH bond. So it only has room for 1 more. So it can't be in the middle of a compound somewhere. It has to be at the end. So that means you don't have to worry about saying 1 propanoic acid or 1 pentanoic acid or whatever, because automatically the carboxyl group has to be at the end. So that's kind of useful. Some important properties about carboxylic acid. It actually acts as a weak acid, as the name suggests, because the proton that's attached here, the hydrogen that's attached here, can actually be lost. And remember, something acts as an acid if it can lose its hydrogen. So that can be lost into the atmosphere, so it acts like an acid. It also has hydrogen bonding, similarly to the alcohol that we talked about. The OH group and the oxygen here allows it to undergo hydrogen bonding, meaning carboxylic acids have fairly high melting points. And because of this overall polar group here, that means your carboxylic acids are also going to be relatively water soluble, because you have that polar aspect that is also going to interact well with water and dissolve in water. So those are some important properties of carboxylic acids there. Now let's talk about esters. This is sometimes a little bit confusing when you first look at it, but it helps to look at the actual process of what's happening. So basically an ester is a combination of a carboxylic acid and an alcohol that are joined together. Often you'll see that esters are referred to as producing a fruity or a sweet smell. And how you actually form an ester is that your alcohol group and your carboxylic group combine together and they produce water to form an ester bond or an ester link. And often you need a catalyst, and in your esterification reaction, which is the formation of an ester, we use hydrogen sulfate as the catalyst, so H2SO4. Something that's important with that catalyst is it should be liquid or highly concentrated. So that's why you'll often see the state being liquid when you see that catalyst present. So let's look at how we actually form the ester, because that will help with naming it as well. So here we have your methanol, so single carbon with an OH group, that's methanol. Then we have propanoic acid, 3 carbons with your carboxylic group here. Now we have an ester form. So how does that ester actually form? So basically what happens is I'm actually going to rewrite this just a little bit so I can make it a little bit clearer exactly what's happening. So here we've got our methanol. And then I'm just going to draw our acid the other way around so we can combine things a little bit easier. And let's just imagine there's hydrogens attached to all of those lines there. So what happens when you form an ester is that the OH from your alcohol combines with the hydrogen from your carboxylic acid, and those two are going to combine together and they form water. In that process of forming water, what happens is this carbon will now bond to the oxygen here. So you get a bond between this carbon and this oxygen, and then you get the formation of this ester bond. So in this ester bond, your COO is coming from your alcohol, your COO is coming from your carboxylic acid, and then your O is coming from your alcohol. So that's how you get that formation of your ester bond. So I think that's really important to understand how that's actually forming, because then it makes the naming easier as well. And then water is basically produced as a byproduct. So knowing how it's formed, do we then name it? Well, we name the alcohol bit first. So how do we know which is our alcohol bit? The easiest thing to do is once you have your ester, you draw a line between the carbon and the single bonded oxygen. And the side with just the oxygen is your alcohol bit. The side with your C double bond O is your carboxylic bit. So we start with the alcohol bit. It's only one carbon, so it's meth. And then we use the suffix YL or il for the alcohol component. So we would say that it's methyl. And then for your carboxylic acid component, we use the suffix OH. And here we can see we've got 3 carbons, so it's going to be prop. And then we need to use the suffix OH, so it's prop and OH. So this ester would be called methyl propanoate. So it's not too difficult as long as you can identify your alcohol bit and your carboxylic acid bit. So just draw a line and identify them separately. So alcohol, acid, OH. Cool. So let's go through a little bit of practice. So I'll give you guys 30 seconds to have a go at naming this, and I'll give you some feedback in the live chat. Let's go through it. Okay, so same advice as before. Draw a line between the carbon and the single bonded oxygen. Now you have your alcohol bit and your acid bit. So alcohol bit, ethyl. So it's going to be ethyl. Your acid bit has 2 carbons in it again, so it's going to be eth. And remember your suffix is anoate, so it's going to be ethanoate. Ethyl ethanoate. Cool. So it's a little bit tricky if you can't identify which carbons belong to which, but once you've done that, it's a bit more straightforward. All right, so now let's talk a little bit about polymers. So polymers are basically when you join together lots of different smaller molecules together, which are called monomers, and you join them all together. This happens through an addition polymerization reaction, where your monomers are heated in the presence of a catalyst, and you form bonds between your double carbon-carbon bonds. And these bonds will then form a chain. So basically what happens is you have, say, an ethene, you add another ethene to it. When they get added together, this bond actually breaks, so then you get a single carbon-carbon bond, but then you can extend the chain out. So what happens is that you go from that single bond of ethene to a polyethene.